Hi, this is the first of several presentations on color. Color is a very complicated subject because we're really interested in how to render colors on a screen or to print colors in a printed image, but we also want to know how people see colors. And the process of people seeing colors, it's very individual. Different people see colors in different ways. And a color is not so much an absolute thing, it's a subjective thing. What color something looks like, what name you give to a color might depend on the colors that are around it, how bright the scene is or the room is, how what you just saw a moment ago. All these things can affect how you perceive colors. So we're not going to deal with that in this course. We're just going to directly talk about colors, say, as displayed, especially on the computer screen, but also to a lesser extent printed on a printed page. And instead, we're going to just deal with the very basic introduction to the theory of color for that purpose. So, at any rate, we're going to concentrate in this talk on how people perceive color, in particular theories of how people see color. And there's basically two underlying theories of color for perception purposes of how we see color. There's the so-called Trichromatic Theory, which is that you see colors in combinations of red, green, blue, and the opponent theory, which says you see colors in contrasts of dark versus light, blue versus yellow, and red versus green. So let's start off with the Trichromatic Theory. So trichromatic means three colors. And this is the sort of familiar theory that people see color as a combination of red, green, and blue. So from combinations of red, green, and blue. And this will be familiar to you just because of the fact that's how we've been representing colors. It's how computers typically represent colors. Trichromatic theory has a long history. The first approaches to it were due to Palmer in 1777. Young further developed this theory in 1801, and Helmholtz in 1850 developed yet further. Grossman in 1853 gave the first sort of full-fledged mathematical theory behind the trichromatic theory. So it's a long-standing theory, more than 150 years old easily. And people see colors as a combination of red, green, and blue. And the physiology behind this, of course, this is only something discovered in the 20th century, is that the retina in your eye has cells or structures called cones. It's got cones of three types. One type is selectively sensitive to reddish colors, one type is selectively sensitive to green colors, and the third type is selectively sensitive to blue colors. So selectively sensitive to red, to green, or to blue. And when I say selectively sensitive, it's not like pure red or pure green or pure blue. It's just selectively sensitive to, so the cones are selective to red, are going to be more selective to wavelengths of light that are around red. So if we have here a graph with frequency of the light waves, and we'll have red to say is about here, green is about here, blue is about here. The visible spectrum is going to be someplace along this part of the graph. And if we were to graph sensitivity, so this is sensitivity of a cone to a light frequency, so we'd have the red cones. The graph of sensitivity will look something like this. The green ones, or green sensitive ones, will look something like this. And the blue ones would look something like this. So what's happening is the red cones are more sensitive to light with frequency in the range of here, green is more sensitive here, and blue is more sensitive here. And then your eye trades off these different sensitivities to estimate, to get a color for the spectrum, or the overall light. There's also, by the way, in addition to cones, your retina has rods. And these are sensitive to light at low levels. The cones basically stop working and don't see anything at low levels of brightness. The rods are, however, sensitive to light at low levels. That's what enables you to see in a dim light setting. And you'll notice when you get up, say, in the middle of the night and it's all dark in the room, these do not see colors, right? The rods we don't have separate rods for red, green, and blue. We just have one type of rod. So if you get up in the middle of the night, you'll notice it's all very dim and gray, and everything is, there's no color. There's no red, there's no green, there's no blue. It's just dim gray color. And that's because you're seeing with your rods and your cones are inactive at that point. So that's the trichromatic theory. So the trichromatic theory is very successful, and we have a physiological reason based on the cones in the retina of your eye for why it works. And you might think, how could there be another theory? But there is another theory, which is the opponent theory of light. Or color. This is due to Herring in 1878. And basically the theory says that people see colors in contrasts of dark versus light or bright. Two is red versus green. And 3 is blue versus yellow. And so there's actually some pretty good evidence for this as well. So in particular, if you stare fixedly at a red object on a white background for a moment, and then turn and just look at a blank white background, you'll see a green floating version of the red object in front of your eyes, right? And then what's happened here is that your eyes have gotten used to seeing the red, and when you turn away, they see the absence of red as a relative green, and so you now only see a green. Physiologically, there is actually also a physiology of this, is the cones send signals to your brain about color on 3 separate neural channels. 3 separate channels of neurons. One channel gives the relative darkness versus brightness. One channel does the amount of red versus amount of green, so how much the red cones are being stimulated as compared to the green cones right next to them. And the third is how much the blue cones are being stimulated versus the red-green cones are being stimulated. So in that sense, we can see just from this that yellow should be the combination of red and green without any blue present, and so forth. And in fact, that's what happens. So we have good reasons for both theories to hold, and sometimes it's useful to think about both, but normally the trichromatic theory is more useful for us than what we typically use. Both theories tell us that visible light, at least, or visible color, at least at normal sort of moderate brightness levels, visible color at moderate brightness levels, right, this is where we can see colors, form a 3-dimensional space. Because in the trichromatic theory, we can vary the amount of red and vary the amount of blue and vary the amount of green in the light. in the opponent theory, we can think of the relative levels of each of these different contrasting possibilities. And that means that when we're designing our imaging spaces for color, we should be thinking in terms of coming close to a three-dimensional light space. Now, this is also borne out by very concrete experiments. I'll talk about that on the next board. So color forms a three-dimensional subspace when you allow, in general, if we fix the brightness level, we basically fix one component of the color's characteristic, and so then we should have a two-dimensional space of colors at some standard fixed brightness. And this stuff has been extensively studied and even measured with some experiments here. And so in the experiments, we put people in a dark room and show them some color. And then you'd like to have them match that color to some combination of red, green, and blue. So the idea is we put a person in a dark room and we shine onto the white wall some color, C, at some fixed level of standard brightness. So it's not too bright, it's not too dark, it's sort of in the normal range of brightness. And then over here, we try to find a blend. We shine another spot on the wall, which is a blend of red, which I'll write with R, green, which I'll write with G, and blue, which of course I write with B. And the idea is we want to match the two colors. And so when we do this, we'll want to come up with something like the following. We want to say that color C looks the same. I'll write equals there for sort of looks the same as some blend. I'll write alpha R plus beta G plus gamma B to say we've got red shining there with relative brightness alpha, green shining there with relative brightness beta, and blue shining there with relative brightness gamma. And we sort of think of alpha plus beta plus gamma equaling 1 so as to get a constant brightness level. Okay, and the experiments show that you can always do this. For any color C, you can always find a mixture of red, green, and blue such that when you add them together, you get something that looks the same as the color C, but, and there's one big caveat here, sometimes some of those coefficients, alpha and beta, gamma, are negative. Sometimes alpha or beta or gamma is negative, as if you were shining a negative amount of red light or a negative amount of green or a negative amount of blue on the circle, which of course is physically impossible. You can't shine negative light on something. In that case, what this means, say if alpha were negative, we'd write C minus alpha R equals beta G plus gamma blue, for instance. And what the meaning of this equation would be if you take the color C plus some amount of R given by minus alpha times R, shine them on the wall together, they will look the same as the mixture of G and B given by the coefficients beta and gamma. All this theory is for the quote-unquote average human of how they perceive color. It's not true that everyone sees colors in exactly this way. A sizable fraction of the population is colorblind, and they can only, the most common kind being red-green colorblindness, where you can't see the difference between red and green. They see colors differently. It's not necessarily always a disadvantage to be colorblind, because red-green colorblind people, the story at least, is that they can see textures better and patterns better, which compensates for not being able to distinguish colors as well. But it is an important thing to keep in mind when designing websites and so on, that not everyone can discern colors the same way. So as a consequence of this, we can draw a very rough sketch of what the color space looks like for colors at the constant brightness. So color space at a sort of constant moderate brightness. The space of visible colors is typically drawn with an image like shaped something like this. And inside it, there's going to be some point that's identified as red, some point that's identified as green, and some point that's identified as blue. And if we form the triangle of these three things, this triangle turns out to be, if you think of red as being the color that your monitor displays with red pixels, green as being the color that your monitor displays with green pixels, and blue as being the color that your monitor displays with blue pixels, these then, this triangle, is the colors that can be represented in the standard RGB model. Where we use, of course, adding up red, green, and blue values to generate a color. This overall thing here, this is the space of visible colors. And you notice there's actually a fair number of colors outside of what your monitor can generate. So there are really quite a lot of colors in the world that you can see, but your monitor can't generate. That's a disadvantage, of course, and there's we'll see in a future presentation, at least briefly, that there are more expansive models for color than red, green, blue that are used for printing or better quality monitors and so on to generate more of the viewable color space, to generate colors from more of the viewable color space. But a standard monitor is only generating a relatively, modest fraction of the colors that you can actually see. And that's it for this presentation. Thank you very much.